worksheet that's actually homework problems on conjugated dienes, which we'll be talking about today, in front of them. As far as things that are due coming up, on Wednesday, the diene nomenclature quiz will need to be taken, and it shuts down on D2L at 11:59 p.m. So make sure you log on before then. Has anybody tried it yet?
No.
No? Okay. Well, hopefully it's working. I think it is. All right, the diene worksheet, which you all just got today, that will be due on Monday the 4th. All right. Let's see, what else? I think that's it in terms of announcements. So, today is a day devoted to conjugated dienes. A conjugated diene, it's going to take some getting used to that. It's a diene, but this applies to conjugated trienes, tetraenes. We could have 3, 4, 5 double bonds. Conjugated ones are a little special because the double bonds, however many there are spaced apart such that you can draw resonance structures. So this right here is conjugated. Something like this, that too is a diene, but these dienes aren't tied together. I can't just take and move these electrons over and push those out. So there's no relationship between the p orbitals of this and the p orbitals of that. They're isolated, they're by themselves. So we call these isolated alkenes. And these are conjugated. So we're going to do our discussion today focused on the simplest conjugated diene, which is 1,3-butadiene. But it's not limited to that. It could work for trienes, and on your homework there are some trienes that you'll notice too. You also can have, you can have conjugated diene-like molecules, but they contain something other than just double bonds. So something like that. And these guys are conjugated as well. And the chemistry we're going to talk about today can even be applied to systems like this. We won't get to that in this unit, but on Unit 2, we'll be going to ketones. We're going to spend a little time looking at how this reacts and actually tie it back into what we're learning today. So there are applications throughout everything. But today, we're going to focus on the simple one, which is 1,3-butadiene. That looks like that. So, recognizing conjugated dienes, what you're looking for is like this guy, we have a multiple bond, in this case double bond, single, multiple. So it's alternating single and double bonds. Okay, if you have more than just one single bond in between, these discussions don't work anymore. Now, in terms of the bonding in this, we need to actually develop a pretty good picture for how bonding is working out in terms of molecular orbitals. So we are going to look at 2 possible bonding sequences. And let's just erase this. So, looking at this guy here. I think I spelled it right. 2 possible bonding scenarios. And I'm going to be focused, I'm interested in the pi bonds, and so that's what we're going to be focused on. If you have access through a computer to a program that can do quantum mechanical calculations, you could actually enter in these 2 pictures that we're going to draw. You could have it calculate the energies of each molecule, and it would tell you which picture is the best one. So it would tell you which one's the lowest energy, the most stable picture. So what you're going to do, and draw it just like I'm doing, I'm going to put carbon, 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 carbon. Then I'm going to put the orbitals. So there's our skeletons of the p orbitals. Now the first picture, we're going to treat the molecule just like it looks. So we draw it like this, and I'm going to say, okay, fine. I've got a pi bond right here. So I'm going to have overlap here and here. There's my pi bond. Then it's a single bond. So single bond, I'm not going to have any p orbital overlap there because there's no pi bond there. Then to the end, I have like that. That is just like the picture looks right there. This is a case where I essentially have two isolated alkenes. And there's no p overlap in that middle part where the single bond is. So that could be the first bonding picture I put in. The second one, I'm going to say, well, you know, I've got p orbitals here. And the electron density could just be a big smear of electron density throughout that long pi system. Because I have p orbital, p orbital, p orbital, p orbital, I could just smear electron density through all the p orbitals. That would be this picture. Looks like that. Now, this is where the 4 pi electrons are in effect delocalized throughout the entire p orbital system. So those 4 pi electrons are delocalized. Now, when you plug these in to computer models and you crunch through the numbers, it turns out one of these is better than the other. Which one do you think is better?
The two isolated?
The second one, actually, yes. This ends up being the better structure. When we were drawing resonant structures back in 420, I think that we mentioned the more resonant structures you can draw for something, the more stable it is. Right? You remember me saying that? What we were really talking about, the more resonant structures I'm drawing, the actual molecule is hybrid of all those, right? So if I'm drawing a bunch of resonant structures, my electrons are smeared over a whole bunch more atoms than they would be otherwise, right? So the more resonant structures, the more delocalized your electron cloud, the less concentrated it is in any one spot, that's a better thing. So this one right here, with the calculations, ends up being lower energy. So according to our models, and this is just computer models telling us this is math, this is better. Okay? But the model is only as good as the people making it, right? So it could be wrong. So we're going to look at some other things now. Let's go ahead and before we launch into, let's just do it right now. We're going to launch into some molecular orbital theory. This is actually kind of fun once you get used to it. You got to figure out how I like this. I'm too tall for it to be down. Okay, there. All right. So this would be kind of case study number 1, deciding on its stability. The second thing, again, is this theory. So we're going to look at an MO picture, a molecular orbital picture of 1,3-butadiene. And we are going to start out, before we actually launch into it, with a little baby scenario. We'll do a tiny one, and then we'll apply what we've learned to a big one. So we will do practice. And we're going to practice on ethanol, which looks like this. Okay? We cannot get much lower than that, right? That's going to be a little tough. So, with ethylene, we have 2 pi electrons. That's all. Now, if I want to draw the ethylene with its p orbitals, I can go like this. There it is. Now, if you remember with p orbitals, you've seen them drawn a couple ways. you have seen in books one part shaded and one part not. Everyone recall seeing that when they showed the orbitals? Okay, another way you can show them is plus and minus. Okay, now what they're saying here is that the p orbital, remember this is a node in the middle. It's a place of 0 electron density. The electron cloud is smeared throughout both lobes. Okay, so when you're looking at where the electron density is, there's electron density there and electron density there, top and bottom. There's just none right in the center. That's why when I was drawing the electrons overlapping to form a pi bond, we always draw top and bottom, right? Because there are electrons in both top and bottom lobes. Okay, they're overlapping. One thing people get confused about is, it's unshaded again, it's the shading, and in particular this causes all kinds of trouble. The plus and minus and the shading just implies that these nodes, effectively they have different signs. When you go through and you're in PChem and you're solving for the shape of a p orbital, you can actually mathematically describe it. Towards the end of the math, there's a square root. And in the math, what are the solutions to a square root? Plus or minus whatever it is, right? That whatever it is, and I've even forgotten what it is, describes the shapes. Okay? One is plus and one is minus. It's just math. Saying the lobes have effectively mathematically different signs. Okay, they're not really different. It's not like when they say plus minus, the electron's living down there. Okay, it's not up there. That's not the case. This is just a fallout from this solving equation. Okay? So, with that being said, let's go ahead and let's do the shading part, because I think that's a little easier to see. Just to show that the lobes are a little different. One's plus, one's minus. So, I am going to take this lobe, and I'm going to shade the top. Now, it's going to interact with this lobe over here. And I'm going to draw it like that. So I have interaction there and interaction there. The way I've drawn it right here, this is a pi bond. So I'll show it as if I'm forming a molecular orbital. So I'm taking atomic orbitals, the p orbitals, overlapping them to form a molecular orbital. It's a pi molecular orbital and it's bonding. So I'm just going to put a little p right there for bonding. So this overlap, essentially the two orbitals reinforced each other in terms of their sign. This would be the same as doing this. Plus, plus, minus, minus. When these overlap, they don't cancel, right? It's a positive reinforcement. So that's going to lead to a bonding interaction. Everyone okay with that? There's no cancel. What's the other thing I could have done?
Plus, minus, plus.
Could have flipped one, right? So let's draw that. That's my other choice. So I'll shade this, and I'll shade that. Now when I look at that overlap, that's the same as doing this. Plus, minus, minus, plus. What's happening right there? Right, they're canceling, right? That is not a positive overlap. I get canceling here. And if I'm having an overlap such that it cancels, it's not a bond. It's not a bonding MO. What do you think it is? It's an anti. This is a bond. So by looking at the different ways I can overlap my p atomic orbitals, I can build molecular orbitals. One is a bonding molecular orbital. The other didn't lead to a bond. It was anti-bonding. Because in the middle, there's nothing. It canceled out. So effectively, I have a node right here. It's a cancel. Okay. Now, if I had just not overlapped these at all, and just left them just the way they are. Let's draw that in. Here's C, here's C. And I'm just going to leave them as atomic orbitals. Not overlapped at all. There they are. There they are. There's no overlap there. This has a certain energy, right? Energetically, it's kind of it's my 0 point, where they aren't overlapped at all. When I overlap the two orbitals and form a molecular orbital, what I'm doing is I'm taking electron density that's localized here and localized here, and I'm smearing it throughout the system instead. So I'm saying I'm going to create an orbital over the molecule, tiny as it is, and the electron density is actually going to be in here. So it delocalizes a little bit. That makes the energy go down. So notice this is below my 0. Okay? When it's anti-bonding, that's not a good thing. You're better off being non-bonding. And so anti-bonding is a little higher. Okay? So, this right here, right there, that's an MO diagram. And when you delocalize electrons, you're able to build a molecular orbital diagram. And now we just have to put electrons into it. I started out with 2 pi electrons, right? When it's non-bonding and they're just sitting here, there's one here, there's one there. This is their energy. When I go to put them into a molecular orbital, their energy is lower overall. So it's better to do that. So with ethylene, I have a filled bonding MO, nothing in the anti-bonding, and this model predicts that should be stable, and it is. So now we're going to build 1,3-butadiene, 4 p orbitals. It gets a little more exciting. There are some points that I want to make before we launch into doing it, because it is a little more complicated. So there are 4 main points. Number 1, as we're doing it, the number of atomic orbitals used is going to be equal to the number of MOs created. I had 2 p orbitals used. I got 2 MOs. If I were doing this with a system of 6 p orbitals, how many MOs would I want? 6. And that's benzene, that's next to you. We're just going to do 4 now. So we're expecting 4 MOs out of our picture. The second main point is that when we can, and pretty much in this class we're going to be doing this, I don't think we sprayed for this at all, that the MOs will be symmetrically distributed above and below the p orbital energy. So that's essentially the non-bonding p orbital energy. That's this guy here when they're not interacting. That's kind of our 0. So if we have a total of 4, I would expect 2 below, 2 above. And the third point. We didn't see it with this, but well, yeah, we did actually. This third point is that as the number of nodes increases, the energy of the MO increases. And we kind of saw it here. This had no nodes, it was low energy. This had 1 node. If I had 2 nodes in my MO, it'd be higher still. Okay, nodes are bad. And then number 4, what they call constructive overlap. That's where the same signs overlap. This is constructive overlap. That's bond. Destructive overlap. That's an antibonding orbital. constructive overlap is going to cause us to have anti-bonding. Let's do anti-bonding interactions. Let's not put orbitals because that's not going to be quite true. You'll see in a minute why I wanted to change that. Anti-bonding interactions. Okay, so with these rules in mind, we'll leave them up and no way are we going to be able to do that. We're going to come over here. This is a big diagram. It's going to take both boards, I think. This will be weird. Yeah.
How come you don't have to put any lines for the pi star, like up arrows, down arrows?
Oh, because I only had 2 electrons in my system, and so I was able to put them in the bonding orbital, and there was nothing in the anti-bonding. If I had 3 electrons for some reason, I would have had to go up there, but I didn't have to. Okay, so here is what we're going to be doing. We are going to take try to decide how I'm going to draw it. Ugh, it's going to be hard. Let's just do it like this. There's one pre-butadiene. And it's based on this molecule right here. Right there. I have a total of how many pi electrons? I heard someone say it. 4 pi electrons, right? I'm going to be doing 4 atomic orbitals, so I should get 4 MOs out of this. And what we're going to do is, we're going to call this our 0 line. So I'm expecting 2 below, 2 above. So let's draw the one that should be the best. That would be the one with no nodes, right? 0 nodes. So all the signs are going to be the same across. So that one is going to look like this. Okay. This one, we have, and I'll write it over here, we have no nodes. It's all bonding interactions. And that's going to be one of our pi bonding MOs. The lowest energy one is the best we can do. Okay, next level up, how many nodes? 1. Okay, we're going to try to keep the nodes symmetric. So if I'm going to do 1 node, the best place to do it is smack down the middle. So let's put that right here. I'm guessing that it's going to be below this line. We'll double check that in just a minute. So draw the p orbitals in. All right, we're going to stick our node right down the middle. There it is. So, this side, we have constructive overlap. That is a bonding interaction. So I'm just going to put a little B right there. We have to do some bookkeeping right now. So I have a bonding interaction. Then there's a node. So if there's a node here, I know this is a destructive overlap. So I can't shade the top here. I have to shade the bottom. So far, so good? Okay, this right here is an anti-bonding interaction. But between the last two, that interaction is constructive again, so same signs. So I'm going to shade the bottom here too. And that is a bonding interaction. So, If it belongs below the line of my zero, which is non-bonding, it should have more bonding interactions than anti-bonding, so net bonding. I have two bondings, one anti-bonding, so the net is one bonding, right? All right, so let's make a note here. I have a net of one bonding interaction. That means that is a bonding MO, and it's below. So I will go by bonding. All right, what's the next one gonna have? How many nodes? 2. Let's keep them symmetric. So we move up here. I'm glad I'm not 5 feet tall. This would be bad. Here we are. All right, 2 nodes. Let's keep them symmetric. I'm going to go there, and I'm going to go there. And here we go. Shade the top. You could, if you wanted to, shade the bottom as long as you're consistent. It doesn't matter. Here, we're going opposite sides. So I'm going to shade the bottom. What's this next one? Shade the top. Good. No, shade the bottom. There we go. Because there's no node. Here?
Shade the top.
Shade the top. All right. I have an anti-bonding interaction, a bonding, and anti-bonding. What's the net?
Anti-bonding.
Is net anti-bonding. And so I'm going to have an MO right here, and I, whoops, I don't want to do that. Put it right here, and I hit my first anti-bonding orbital. Okay, pull this guy down. Now we get to the final one. The top one is always the worst it could possibly be. So, on this one, here's my orbitals. I'm going to have nothing overlapping constructively. So I'm going to go top, bottom, top, bottom. The number of nodes, 2, 3 nodes. So it went 0, 1, 2, 3, and energy. Here it is, anti-bonding, anti-bonding, anti-bonding. That is clearly an anti-bonding orbital. And so you will go by anti-bonding. And there it is, parallel diagram. Just like that. Okay? This is a really fun one to build for benzene because the orbitals are circular, but they're in a cycle, and there's 6 of them. It's very interesting. All right. I got to put in 4 electrons. 1, 2, 3, 4, and I'm done. So I put my 4 electrons in. They all go into bonding MOs. That's good. And look at the energy. If I had left them just in their atomic orbitals without interaction, there they are. I'd have electrons at this energy level, right? But by having all these p orbitals interact together, all of them had to build this picture because it's the molecule, they actually are lower in energy. So what I have is they are net lower in energy when all 4 p orbitals interact. So this MO picture agreed with our earlier one, which would come out of the computer, saying, yeah, it is lower in energy when you can distribute electrons over a whole system instead of having them isolated. It's nice that two models agreed, but they could still be wrong. So now we're going to go and look at two pieces of actual physical evidence that really do point to this being the case. All right. The stability due to this extensive conjugation is seen in heats of hydrogenation. So we need to quicken review the hydrogenation reaction, I think. So our third piece of evidence. All right, a hydrogenation reaction. I have a double bond, and what am I adding to it? H2. And what else is needed? Yeah, some kind of catalyst. And I put hydrogen there, so I'm going to an alkane when I do a hydrogenation. So that's a hydrogenation reaction, and there's some kind of heat that's negative, so heat's released. So if I wanted to draw it in terms of almost graphically, I would have the double bond higher in energy than the single bond. And if I had energy going up here, I could draw the energy levels. And when I turn this into this, my heat release is just measured by whatever this difference is. And we looked at this in 420 a couple of times. So, what we're going to do is we are going to give you guys some numbers now. And, yeah. Let's go over here. I'm going to give you a reference, and then we're going to see what's happening with the one we give you running. So, our reference number is this. 4 carbons, 1 double bond. When you hydrogenate it, delta H is negative 30.3, and this is kcals. Ancient units, kcals per mole. So, you would expect with 2 double bonds going to the same exact thing, delta H would be negative 60.6. There's 2 of them, you should get twice as much heat out. And that seems pretty reasonable. Really, here's what you get. Delta H is negative 57.1. And those are all kcals per mole. When I was at Berkeley doing undergrad, they would put up these things. They loved putting up these heats of hydrogenation. And the guy put it up, and he'd move on. And I'm in a room, there were 600 of us in my OChem lecture. And I'm in this room, this meant nothing to me at all, these numbers at all. I noticed them, I'm like, okay. And everyone around me isn't saying anything, is who's going to speak up with 600 people in there. And I figured they all got it. And no one got it. So these numbers meant nothing to me. But if you put them in a graph, it really does help out. Once you can see it, I think it means quite a bit more. Go like this. Here's energy going up. Things that are higher energy are less stable. So, let's put in our isolated one. And this is isolated. Going down to the level of the alkane, the isolated one, you would expect would release 60.6. That's what we guessed from our baseline. It didn't release that much. So what that means, if it didn't release quite this much, it meant that the real one, which we can draw like this is the conjugated one. It has to be lower in energy. It goes to the same place, it's got to be lower. And this difference here, between here and here, that's the lowering in energy you get from that conjugation throughout the whole system. So, this guy, being conjugated, caused 3.5 kcals per mole more stability. So smearing that electron density throughout the whole system led to about 3.5 kcals per mole better stability. Remember that number for benzene, because it's very conjugated as well. Okay, so that's good. That is physical evidence that agrees with all of our theoretical stuff we've done that says, yeah, the picture is actually like this. This is some evidence that says, yeah, it isn't just a double bond and a double bond. It can't be just that. There's something better about it than that. I saw a hand up somewhere. Yeah.
When I was reading the book, I thought isolated double bonds had to be like more than 2 bonds away, or
They technically do. What we're doing with this is we're forcing them to be isolated. So I'm looking at a picture, 2 extremes. I'm saying, okay, we know, just from our experience, that this is the correct case right here. But I'm saying, okay, I'm going to force there to be no interaction, so I'm going to block that off. And when I do that, this is what I would expect the thing to look like. It clearly doesn't look like that. Okay, so I'm forcing them to put the isolated, if you want to, in quotes. Because we are saying, okay, if there's no interaction, this is what it would look like. Well, we know that's not true. All right, the fourth thing. Then we're actually going to start some chemistry. This one is bond lengths. When you measure the bond lengths, you also see the fact that something's going on there in the middle. And make sure I have the numbers. Here we go. In terms of bond lengths, a double bond is 1.33 angstroms. A single bond is 1.54 angstroms. If you take 1,3-butadiene, which we draw as double, single, double, it should be 1.33, 1.54, 1.33. But we know there's some double bond character here. And so what you actually have is in the middle. It's 1.47. So it's short. This is shorter than a single bond. And that's telling you that it has some pi bond characters, has some double bond character. What would you expect the double bonds to be?
1.33.
Yeah, they're not really true double bonds, right? They're sharing some electron density, so they shouldn't be as tight, not quite as short. The difference is not so impressive here. 1.34, it's a little bit longer, but it's not nearly as impressive as what's going on right there. All right. The fact that you do have conjugation really can change how these guys react. Their reactions, when you do addition reactions, are a little bit weird compared to an alkene. So, let's take a look at the one we're going to study for the rest of the day and see why it is so different. An addition reaction, just to refresh your memory. So you have that guy, just an alkene. And we add, we're going to be doing this all with HBr, so we'll add HBr. Do you remember the mechanism for this? Yeah, what happens first? double bond attacks the H plus. And I'm going to add a hydrogen and have a plus. What do you think about that? You like that one? No, yeah. I have a choice. I could add it like that, or I could add the hydrogen to the carbon. It's not substituted. And put it like that. The second one's better. Why is that? It's more stable. Why is that? There's the inductive effect of that added CH3. So this CH3 is electron donating inductively, and it can help stabilize this electron for carbon right here. Okay, so we don't see this guy. But we had a name for this. It was somebody's rule. Markov-Markov's rule. Good. And then what happened is Br minus came along, attacked. And we got that. That is an addition reaction. So it followed Markov-Markov's rule. Well, conjugated dienes, conjugated trienes, anything conjugated, doesn't quite do it this nicely. So, let me show you what happens, and then we're going to have to explain or take some time explaining why in the world it's happening like this. So, let's do 1,3-butadiene. We'll add HBr to it. And we're just going to add one equivalent, by the way. So enough to react with one of the double bonds. And I get that. Hopefully that makes sense. This is straight out Markov-Markov addition. And I get that. That's weird. And the really fun thing, because we can explain this, this will take me 1 minute to explain this. A lot of you guys probably see why that is right now. That's not the fun thing. The fun thing is it's temperature dependent. So which one I get predominantly depends on what temperature I run it. And the really fun thing is that sometimes I can turn one into the other. So if I heat it up, I can do one thing. If I cool it down, it doesn't work backwards. So it's like an equilibrium between these that's kind of affecting what your ratios are. That's the hard part. So let's first give these names so we don't have to keep drawing them over and over. These names are not like related to IUPAC. Okay, we're just going to designate the carbons that are reacting. I'm going to call this one right here the 1,2 product. That's because I reacted 1, 2. Okay? Take a guess what this one's called.
1,4.
It's the 1,4 product. Good. It's 1, 2, 3, 4. Okay? It's not the IUPAC name, so don't worry about it. I'm just designating which carbons reacted. So I have the 1,2 and the 1,4 product. All right. The 1,2 product, I think we see where that came from. Where did the 1,4 come from?
Resonance.
From resonance. Good. So, when you add the hydrogen, you initially, there's your H, there's your plus, right? But we just talked about how that high electron density is smeared throughout the whole system. So I can draw a resonance structure where I bring those electrons over, and 2, 3, 4. There's a double bond in the center. Here's my H, and here's my plus. Now remember with resonance structures, it's not going one to the other, one to the other, right? It's the actual intermediate is a hybrid of the two. So what we're really looking at, we're going to use these pictures to explain what's happening because they're just emotionally easier to deal with. I need the plus to be somewhere. But what's really going on is it really is like this. I added my H. I I have electron density all in through here, like that. And I have a delta plus there. And I have a delta plus there. That's what's really going on. I have two carbons with partial positive charges, and the Br minus is attacked in either place. Okay, but in terms of drawing a mechanism, I can't deal with this at all. So we'll draw one or the other. Okay, just keep in mind it's not flipping back and forth. Okay, so this one clearly gives us the 1,2 product. And this one gives us the 1. That was easy. Here's the fun. I'm going to give you guys some information. All right, here's your information. If I take the 1, 2, and I treat it with excess HBr, I can turn it into the 1, 4. So the 1, 2 can be turned into the 1, 4. The 1, 4 can't be turned back into the 1, 2. Now, in terms of stability, what does this tell you about the 1, 4?
It's more stable.
Right, I can turn things into it, but I can't go backwards. So the 1, 4 is more stable. That's going to be important for a graph we're going to build in just a minute. Now, when we talk about how it's temperature dependent, all right, we're going to build a chart. Leave yourself space. All right. Leave yourself like a little box. Put this in the middle of it. We're going to go up, and then we're going to go down like that. All right. If I do this reaction cold, let's go to the extreme, negative 80 degrees. I get 1, 2, and I get 1, 4. The ratios, when it's cold, 80% 1, 2, 20%. When I do it warm, let's go to 40 degrees. It's not like boiling hot, just slightly warm. I get 1, 2, and I get 1, 4. The ratios flip. I get 20% 1, 2, 80% 1, 4. That's a little weird. Then it gets even more fun. If you take the product ratio when you run it cold and you heat it up, you can go that way. So I'm going to heat it up, and I can turn it into the ratios if I had done it already. If I do the reaction warm, I get these ratios right here, and I cool it down to negative 80.
Go back.
Nothing happens.
Okay.
Isn't that fun? So that's what we're going to explain. And the way we do it is with one of those potential energy diagrams. I'm going to do it kind of spread out. Some folks do it with one right on top of the other. I can't see it very well that way. So we are going to have typical potential energy diagram, energy increasing here. And this will be reaction progress, going this way, and we're going to be going that way. All right, so just to kind of give you a basic skeleton of what it's going to look like. I'm going to start out with the carbocation intermediate, kind of right in the center. So this will be H, and we'll do the one that's emotional. That one right there. Okay, and I'm going to put it at that level. That's what that is, it's my intermediate. And then what we're going to do is we are going to put the products in there. We're going to put the 1,2 product and the 1,4 product. I'm going to do the 1,2 product on this side and the 1,4 product on this side. Now you guys just told me from a piece of information a while ago that the 1,4 was more stable. So I'm going to put it lower in energy. So here's the 1,4, and I'll put the 1,2 up here. Okay, so far so good? All right. Now, we have to draw in, and don't draw this yet. As you guys know, it doesn't just go like that, right? We went over, and it's like that. We had to go over a transition state, right? A point of high energy. So, I have to draw like this, and don't draw this, and like that. Something, okay? This, I'm very happy with this part of it here. The problem is I don't know how high this should be and how high that should be. Right? I don't know which one's higher right now, so we have to go back and think a little bit. So looking at this guy, this actually tells you the answer. The one that is lower, let's say, I don't know, let's say this was the lower one and this was higher, so it's like that. Which is going to form faster, if this is the correct picture?
It was lower.
The 1,2 would form faster, right?
1,2.
We're all starting at the same intermediate. This is the path of least resistance. So I should be able to form 1,2, if this is right, much more easily, okay? When you're running a reaction really cold, what don't you have a lot of? You don't have a lot of energy, right? So you are going to be following the majority, the path of least resistance. So if it's really, really cold, you're going to get most of whatever is easier to form. Which one is that?
1,2.
The 1,2. Yeah, this is cold, not much energy. The 1,2 formed more easily. It was faster. That's what this told us. 80% was 1,2 when it was super cold. That means the little hill to get to the 1,2 must be pretty darn low. So I have the wrong picture. Let's fix this guy. So the 1,2 is low, not in the right picture. And the 1,4 is high. Does that fit so far the data that's up here? It's cold. It's going to be easiest to get to 1,2. That's what I see most of. Okay? Good with that picture? All right. So we've explained this. What we have not explained is anything else on this thing. So let's talk about when it is warm. This is kind of fun. When I run this warm, imagine taking snapshots. If I run it warm, what am I going to form first? Most of first. It's warm.
1,4.
It's still 1,2. Right? 1,2 is easiest to form. It is always going to be easiest to form. So when I run it warm, 1,2 forms first. I will get some 1,4 because some of those molecules will have enough energy that they can form 1,4, but not very many of them. Okay, so 1,2 will form first. I'll get some 1,4. But still, it's easiest to form 1,2. But what happens when it's warm is, let's say I start out with 100 of these guys. And initially, 80 go there, 20 go there. That's just like if it was cold, right? When it's really cold, though, look at this distance here. To go backwards, let's draw a line across. To go backwards, I have that much of an activation energy, right? So when it's cold, they go where they go. Can they ever go back? Can I ever reverse this? And everything would really like to be 1,4. When it's really cold, 80 of them form 1,2s. But they're never able to get back over this high activation energy when it's cold. When it's warm, though, there's a lot of energy being supplied. So 80 go here, and this isn't so bad to go backwards. And so what they can then do is they can go backwards. So at warm temperatures, this reaction is reversible. And the 1,2s go back to the intermediate. When it was really, really cold, the 1,2s formed, and it was like being trapped in a pit. They couldn't go back. So this was irreversible. And the reaction was stuck. It was stuck here at these ratios. Not the case when it's warm. So some go back in our favor. So let's say when they go back, and take a different snapshot in time. Let's say they go back, they redistribute. And let's say of the ones that went back, maybe now there are only 60 here. The other 20 fell down here. So this climbs up a little bit. That's now 40. Well, it's still warm. These can still go back, right? And so they go back to the intermediate, and then they redistribute again. Most of them come back to this. Some go back here again. So maybe this climbs to 50, and this climbs 50. And then 10 minutes later, after this keeps going on and on, well, this is now 60, and this is 40. You get what's happening? What happens to the guys that go to this side? Is that reversible?
No.
No,
They
they
stay
would have to
there.
have an activation energy that went like that. What are the odds of that happening?
Slim to none.
Like slim to none, right? So anything that comes down here is stuck. Maybe if you heated it really, really, really hot, you could start getting these guys to go backwards. But at temperatures that are warm, this can reverse out, and eventually the 1,4 is going to kind of act as a sink. It acts as a low energy sink. It takes time to do this. If you were to let it go for a minute and instantly cool it down, you wouldn't see these ratios. You would see mostly 1,2. If you let it go for time, it'll eventually work itself through to where there's more 1,4. All right, so the key is, when it's warm, it's reversible, the 1,2 part is. When it's cold, nothing's reversible. They go where they go, and that's it. They're stuck. Okay, Gabe?
Oh, you answered.
Okay. All right, you guys good on that idea? Okay, they have some words for this. This one is fast. It's controlled by, the ratio is controlled by who forms the quickest, right? Which was the one with the smallest activation energy. This is under kinetic control. It's dictated completely by speed, not by stability. And the 1,2 product, they actually call that the kinetic product. The kinetic product is the one that forms fastest. The bottom reaction where it's warm, that was dictated by stability, right? Our product ratio was dictated by stability. And we ended up, given time, getting mostly the more stable one. So this one is under thermodynamic control. It's thermodynamic control. The 1,4 product is the more stable product, and it's called the thermodynamic product. You have to be careful. The kinetic product is not always the 1,2. You have to actually look at a reaction and think about it before you spit out what the kinetic product is. A lot of the times it is the 1,2. but on the worksheets, and I think on the practice test, I try to trick you, and that's not necessarily always the case. Okay. Now, can you explain to yourself, let's do this business here. If I take the reaction mixture when I run it cold, okay, I get mostly the 1,2 because it forms fastest, and I heat it up. Does it make sense to you that the ratio would change to favor the 1,4? Does that make sense? What am I doing when I'm heating it up? What am I supplying?
Energy.
And I'm making what was irreversible, reversible. And then it can start to work itself through, right? So when I do it warm, and I get mostly 1,4, so let's say I let it sit for an hour, so it works itself out. I get this ratio, I cool it down. Does it make sense that it didn't revert to the other ratios?
Because there's
When
no
I
energy.
cool it down, what am I doing to it?
You're taking away energy.
Stopping it, right?
Stop.
So I'm making it irreversible at these ratios. So the minute I cool it down, when I've got 80 here and 20 here, I cool it down, I've stopped everything. I'm locked into those ratios. So really it's more of a question of, is your reaction reversible or is it not? What's causing these ratios? Okay, so you guys have on your worksheets, let's discuss this thing right here, a bunch of questions about this concept and a bunch of examples. And there's some things I want to point out to you so that you don't give me like 10 million products to be turned in. So let's talk about, in particular, number 4. Number 4, we're going to apply this to some examples that are a little more complicated with substituents on them. And we just kind of walking through 4A, give you an idea of what I'm looking for. What makes this a little more complicated is that with 1,3-butadiene, this one, it didn't matter if I started my reaction with this double bond or with this one, right? They were the same. Here, it's not the case. This double bond is different than this one. So we're asking you for, in number 4, kinetic and thermodynamic products. And so you're going to have to do 1, 2, and 1, 4. You'll have to look at those mechanisms. The problem is, if you start with this double bond, you'll have a 1, 2, and a 1, 4. If you start with this double bond, you'll have a 1, 2, and a 1, 4. And it becomes very hard to answer this question because you could have two different, essentially, trunks coming down. Does that make sense? Here's what I want you guys to do. We're going to add HBr. Let's take a look at the choices. If I add it here, and we're going to pick the most stable thing, H plus. It could look like that, right? My intermediate. I'm not going to choose, and don't choose this. Don't do this for starters. Okay, does everyone see why that would not be one of my choices? Okay, that's the least stable thing I could have done. Don't do that. So let's do this. So that's a choice. Or if I did the other double bond, I could do H plus. Or I guess I could do. So this is the first thing you have to do, is you have to draw out the reasonable possibilities for your initial reaction. Now, let's stop and think for just a second. One of the 3 up there, there's clearly the very bad one, which we got rid of anyway. One of the 3 up there is not good. First, second, or third? Third one, what's wrong with it? It's not conjugation, right? So this one here, I could move this double bond over and I could delocalize that positive charge. Same thing for this one. I can move this down, delocalize that positive charge. This one, there's no conjugation. So this intermediate is going to be pretty high energy. It's not very stable. And when you're forming your intermediate, this one's going to have the highest energy of activation. You're not going to see it. Okay, so we can also get rid of that one. That leaves us with two. One will form preferentially over the other. Which one's the better one, first or second? The first one. How come? Tertiary allylic carbonation, right? This is the one, ding, 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 that you want to work off of. Give me the products for that one. So on number 4, first figure out which is your absolutely best intermediate. That's the one that's going to form. And then do your problem from that. Okay? So you have to think a little bit before you launch into it. And then vial number 6. Let's talk about that. Number 6 gives everybody trouble. So I'm going to give you some hints. On number 6. Okay. What it does is it gives you a bunch of products, and we want mechanisms to explain every single one of them, and also explain the ratios, their percentages. So, what we have with number 6 is we have bromine, which is the thing that's going to react first. You guys remember, if I took that away, remember the bromonium ion? Okay? So, this guy would attack bromine, and just ignore that bottom part for now. You guys all drew that. Remember that? Okay. And then Br minus came and attack. So the bromonium ion helps to explain some of what's going on. But you'll also see that somehow OCH3 got stuck onto some of those molecules. So, yeah, a lot of it. You've got a competing nucleophile. You have methanol and you have Br minus. So you've got a competing nucleophile. So you're going to have to deal with that. That explains some of the products. Now, in terms of mechanism, you are far better off if you don't draw the bromonium ion. Draw it like this. Okay? You'll be much better off if you do it like this. The bromonium ion was really just a resonance structure of this. Draw this and do all your mechanisms from that. It makes it a lot easier. Okay, so draw it like this, competing nucleophile, and then here's something to think about. As you go through, you have Br minus versus CH3OH. Methanol is the solvent. As you explain the ratios, ask yourself a few questions. And don't answer them right now. Number 1, which is the better nucleophile? Don't scream it out. And number 2, which is the more prevalent, meaning more of, which is there physically more of, which is the more prevalent nucleophile? As you're trying to explain those ratios, keep these 2 questions in mind. Okay, they're key to explaining the ratios that you see. Okay, that is a fun problem. It's the best one on the page. If you can answer that one, you got a good handle on what's going on. All right. I have you for a few more minutes. What I want to point out to you, in case you have not noticed it, I don't know if we mentioned this last time or not, but on Wednesday, February 6th, you guys have a review quiz in lab. And the review quiz is going to cover alcohols and alkenes, the reactions of them. What it's going to be is 10 questions. it's structured just like the ones last semester were. I might give you, well, let's say something like this. And you have to tell me what goes right there. Okay? It's pretty critical for what we're going to be going into after we finish up this chapter that you remember these reactions. We're not going to talk about them again, but you're going to use them all the time. And if you're weak on them, it's really going to cause you trouble. So over the next week and a half or so, you need to go back and you need to review your alcohols and your alkenes. Alkynes we'll probably never use, and so we're not going to focus on those. And remember, if you can do alkene reactions, you can do alkyne reactions. So go back, there are no notes on it, okay? You have to know it. So no notes, it has to all be up here. I know.
Thank you.
Yeah. Oh, you guys, and keep an eye on D2L. There may not be lecture on Wednesday. There will be lab for sure, but I may have to go somewhere between 11:30 and about 1. And if that's the case, I'll put it on D2L, and we'll do the Diels-Alder material in the Diels-Alder experiment. It fits in there just fine too. Okay, so keep an eye on D2L, just in case I'll be gone. But